So here we have a question that's asking you to consider and try to find the stationary points and determine the nature and then the points of inflection. And before we discuss about the solution of this question, it would make sense to give you a little bit of a reminder about the stationary points and the points of inflection, what they are and what they look like, and so on. So the stationary points are essentially they have three names altogether. You can either refer to them as stationary points, or as extrema, or as maximum and minimum points. They all mean the same thing, so be aware of that. If they ask you to calculate one or the other, that doesn't all mean the same thing. And the way we calculate that is by doing the following. So you will the first step you cannot avoid it. So step number one, you're gonna find the points for which the derivative of the function is equal to 0, because the gradient for every single one points that you see on this graph here is going to be equal to 0, right? You can see there that they are parallel to the x-axis. Gradient for ants means the derivative to be equal to 0. So that's step number one, cannot really be avoided. And then the second step can be differentiated. So as kind of like, logic, you will either create a table of values, and you've seen this perhaps before, but that's going to be something like that, the study of the first derivative, and that would mean for the actual function, whilst here we have the number line from negative infinity to positive infinity. And then we will do a couple of examples. So let's say 3 was the root of the first derivative, then let's also assume that it's the first derivative is positive here and it's negative here. Then that would mean that the function would have been increasing here, will be decreasing here. So that point would be a max at the point 3, f of 3. That's the logic. I'm not using a specific thing. It's just to describe the whole thing. The other thing you can do in order to determine the stationary points, it will be so that's the step 3. Well, it's a bit of a misconception. It's either or. So that would also be a step 2. Once you find the roots of the first derivative, would be to use the second derivative test. And the second derivative test says that if the second derivative is positive, then you have a minimum, right? Intuitively, it's a little bit kind of like, counterintuitive. It seems like it's working kind of like, because the bigger would correlates with the max, or maybe just in my head, but you know what I mean. And if it's negative, it's going to become a maximum. And this is what we are trying to do for this exercise down below. So here I am I'm halfway through the step 1, and the step 1 is the step we just defined up here at the top, right? Which means like find the first derivative and find the roots of the first derivative. I've already completed the product rule for the first part. So what you see here is essentially the product rule. You feel free to pause the video and sort of kind of like, try it yourself. And I want to find the roots. And although it's tempting to expand the brackets and create a polynomial, that's going to become kind of like a little bit of a nightmare. Assuming that we are working in a no calculator paper, then we might as well collect the like terms rather than. So, or what they have in common is going to be the x minus 1 with the square from here, and then the x minus 4 to the power of 2. So that's what you're going to be left with. These are the common kind of like, parts, because factored form would be easier to put it equal to 0 and find the roots. So in an attempt to kind of like, make this video not way too long, I went ahead and I factored the first derivative. Remember, we're still doing the part 1. We found the first derivative, but now we're going to find the roots of the first derivative. So the first derivative is going to be equal to 0. That means that all of that has to be equal to 0, and the roots that we get is like the x is equal to 1, x is equal to 4, that makes 0 the second bracket, x1 the first bracket, 4 from the second bracket, and from the first bracket we get 11 over 5. And these are the three roots that we have for the function. Please, please, please be aware, we had this conversation before, that root here has a multiplicity of 2, which is even. Therefore, there will be no change of sign on either side of that root for the first derivative. So we're not going to have either a minimum or a maximum, or otherwise it will bounce at x is equal to 4. So for the second step, I have the options of either doing the second derivative, but let me just focus on what I have for the first derivative, and this is what I have here. So if I want to find the derivative of that, it's going to be pretty painful. So I'm not going to use the second derivative test because it's not very handy in this case. So what I'm going to do, I'm going to construct a table of values. And let's go and do that over here. So the table of values, you have first the number line for the values of x. Then you have a line where you put the information you know about the derivative of x, and then the interpretation of what it means for the value of x. So you start with negative infinity. You have to make sure that you put your the roots in order from smaller to biggest. So here I'm going to have 1, and we have 0, the derivative for 1. Then it's going to be the 11 over 5. 2 times 5 is 10. Now I have 11. It's going to be the 2.1, right? So I'm going to put it on the right-hand side, and definitely smaller than a 4. And here we are. And then we're going to have to complete the sign of the function of the sign of the first derivative. By sign, we want to test whether it's positive or negative. That's what it means. So now I have my derivative function for which I'm gonna test for the sign, right? Signs. And then the table, or the sign table, because that's what I'm doing. This is the sign table, and it's right below. And the idea is for me to test what happens for values x is bigger than 4. Use a convenient value that's bigger than 4 and says to calculate, let's just say 10. And then the f of 10 would become, 10 minus 1, that's going to become 9. 10 minus 4, that's 6 squared. Let's put it here. And then 50 minus 11, that should give you a 39, which is positive. So I know that my function is positive here. Now I know that 4 has a multiplicity of 2, which is an even multiplicity. So what that means, let's assume that this is like number 4, or any graph. In this case, we're talking about the derivative function, right? But if it was coming, let's say, towards 4 and touching the x-axis, it will not cross, it will bounce. So it would be somehow like that. So if that was the derivative function, it will be positive left and right? Whilst if it was negative, but we know that it's positive, then it would have been negative on both sides. So this is going to be positive. And then just by checking the multiplicities for 1 and for 11 over 5, this is when it's going to cross. So here it's going to cross from positive into negative, because it has to, right? At 2, oh no, 11.5, I'm sorry, 11.5, so it's going to cross and it's going to go into negative, and then at 1 it's going to come back and it's going to go back into the positive. And this is how, that's a quick way to complete a table of values. But you can also pick up specific points, so a point that's bigger than 2 but smaller than 4, let's say for example 3, and test if that's going to be a positive here. And then you could do the same between 1 and 11 over 5, so you could choose 2 to test if this is going to be negative, and so on and so forth. Now what that means about my function, this is the study of the sign of the derivative function. That means that my function increases from negative infinity to 1, then decreases from 1 to 11 over 5, then it increases again, and then it increases again. And don't forget, for all of those 1, 11 over 5, and 4 is where my derivative is going to be equal to 0, right? So I have a maximum point here, and the coordinates of the maximum point are going to be, let me just make some space here by deleting that part because we don't need it anymore. So the maximum point is going to be the 1 comma f of 1, and you can plug in the value of 1 in the original function and find what's the maximum value. Here I'm going to have a minimum value, which is going to be the 11 over 5 comma f of 11 over 5. And then at x equals 4, I have just a stationary point. Stationary point that it's neither maximum, neither minimum. And I will refer you back into, let me just go back into the point that we have here, right? Remember that we have a local maximum here because it could be a global maximum, then we have a local minimum, and here we have a stationary point. And in our case, for x equals 4, that's what we've got. We got a stationary point that has a derivative equal to 0, but it's not neither maximum or minimum. That's for the part 1. For the second part of the question, we need to talk about the points of inflection, but we cannot talk about the points of inflection without talking about concavity. So let's just see what's happening here. Concavity is the curvature of the curve. So if you imagine that you shine a line on this sort of side of the graph, and then that bounces back, then that would bounce back this way, right? That's why it says here concave down, and that in terms of a function happens when your second derivative is smaller than 0. I know it probably does not make sense now why, when the second derivative is smaller than 0, concave down. It's for a different sort of moment to give you that explanation. And then you're going to have to accept it now for that question, and then it concaves up when the second derivative is positive. That's the concave up. So there is a point here in the middle for which the second derivative is equal to 0. But essentially there is a point that we have a change in concavity from concaving down to concaving up, and that's called the point of inflection. It's the point where the concavity changes, and then it goes from down to up or up and down and vice versa. So if we put all this information in some sort of step 1, step 2, step 3, for the first step, you're going to have to find the first derivative. Step 2, you're going to have to find the roots of the second derivative or solve the second derivative is equal to 0, which will provide you with the possible points of inflection. You still don't know if the second derivative is 0 that you're going to have a point of inflection. To have a point of inflection, you need a sine table to change in concavity. So I did try to make my life easier in order to find the second derivative. So what I did, I just expanded those two brackets, and I tried to create an easy polynomial. So when I apply the product rule, I don't have 3 different functions, although I could have 3 different functions too, and I will do it now to gain some experience from that. So having 3 functions doesn't really change anything. I'm going to have the derivative of the first one times by the second one times by the third one plus the first bracket times by the derivative of the second one times by 5x minus 11, and then plus the first one, which is x minus 1 times by x minus 4 times by the 5x minus 11 derivative. And then I would have to find the roots of that, but that's definitely going to be a calculator part, so I'm going to stop it here. And I will find the second function to show you how the concavity and the points of inflections work. That's it for now.